Welcome to the second part of the capacity transfer sessions from the work undertaken within the SUSTRACK project. Today, we're going to be focusing on systems thinking and system dynamics and their specific applications within the SUSTRACK project. Now, systems thinking and system dynamics are system methodologies that were invented back in the late 1950s at MIT. Originally, they were mainly applied to engineering topics, but in the last 70 years, that applications have started to spread out to be more diverse, focusing on psychology, politics, environmental economics, so on and so forth. Now, systems thinking is an attempt or a methodology that attempts to understand a whole system rather than its parts, meaning that instead of just focusing on, let's say, an economic application, we're trying to connect that to environmental, social, and other parts of the system that do interact with each other. We do so to be able to then utilize the most effective leverage points to either stimulate the change we want to see in the system or avoid unintended consequences from, for example, policy interventions. Now, if you look at the shape on the left right here, you can see that there's a certain amount of potential triangles there, right? Maybe there's a triangle within this black shape here. Maybe your eyes are drawn to this bigger sort of white one here. And of course, some of the eagle-eyed among you would probably notice the one within the Pac-Man's mouth. Now, the answer to how many triangles there are is, of course, none. There is no single connection between all of these. And what we are doing as humans is we're simply inferring that we think there are triangles there, and therefore we're connecting the dots in our brain. In a way, what we're seeing is we're seeing an event above the surface without understanding how our deeper understandings of it work. To sort of apply this in a more academic sense, what we are seeing are the events. These are things that are transpiring, that we can see, that we can measure. For example, it could be a pen falling, it could be raising tax rate, or as we're the example we'll stick for in this case, it could be a car crash. So if the car crash is the event, then what leads to that event? Well, there could be certain patterns and trends. Maybe that in the last 2 to 3 years, the area where this event or car crash happened, maybe there's been a lot more speeding going on recently. Well, why is that pattern? Why is that pattern sort of occurring? Why are people speeding more? Well, if we go sort of further underneath towards the bottom of the ocean in this iceberg analogy, we can start to connect some of the systemic structures, meaning that maybe the specific part of the road feeds into or feeds off of a highway, so people are speeding and struggle to slow down, or there's a red light at the end of the session that people really want to cross, but it doesn't stay green for long, so people try to speed to sort of get past it. Well, if we're talking patterns and trends into sort of the infrastructure that allows these pattern and trends, there's a second component, and that is the third component, that is the mental models of the drivers in this case. Maybe you work right at the other side of that intersection and you don't like being late, so therefore you're trying to speed up more and more. The mental models are effectively the perception and ideas of each of these drivers that causes these patterns and trends eventually leading to the event that is the car crash. Now, we usually have data for the event, but we might be lacking some from the patterns and trends, unless, of course, there's a speedometer in this case, but we definitely don't have the systemic structure nor the mental models. And therefore, system dynamics and systems thinking is often about trying to connect all of these mental models, systemic structures in a way to create a common understanding between participants. And this is often done through a co-creationary way. Now, to be able to sort of make this clear, we'll go over a quick example focusing on sustainability in this case. So on the side here, you'll see two pictures. On the left one, the left upper picture is a picture of a river in Vietnam. Now, in terms of sustainability, this is usually measured through the SDGs or the Sustainable Development Goals. So we'll try to judge these pictures based on said goals. Now, if we're looking on the picture, you might see a lot of fishermen. So maybe there's zero hunger or doing really relatively well there because there might be a lot of food. There's a village there that could probably mean there's clean water and sanitation, probably more decent work and economic growth. But there might be overfishing because, again, there are a lot of fishermen there. If we look at the bottom right, this is a picture of somewhere in the Caucasus, sort of a plain field. We do see some village down in the background, but generally you wouldn't describe this as a very developed picture. You can probably imagine that it's a lot of green. So if we're comparing this in terms of sustainability goals, it'll probably do really well on number 15 with life on land. And if there is water, it might be life below water. Number 14, but less so on decent work and economic growth, maybe not as well on affordable, clean and energy. If we continue upstream from the river to the left, we eventually reach a hydropower dam. Now, that hybrid diagram, even if it is gray infrastructure, is required for some of these aspects, right? If we want affordable and clean energy, well, hydropower is a relatively clean type of energy. Maybe that infrastructure itself and that energy allows for more decent work and economic growth. But at the same time, if we take this sort of a situation to the extreme, if you look down to the right, that is a picture of New York City, where there is much more gender equality, quality education, good health and well-being, but you may not want to, let's say, drink or swim in the Hudson Bay, right? What we're trying to get to is that integration is very important when it comes to these topics, because growth in one area will have unintended consequences elsewhere. So if we take this simple population development model, we say that if we increase population, we'll then have more gross domestic product, which is really good. People are getting richer. And that might cause people sort of reinforcing that loop. But at the same time, the more population we have will need more agriculture. Well, let's say we start to meet that demand. Well, that starts to come at the cost of forest, of water quality, biodiversity, fishing, and so on and so forth. So in the end, a positive growth in one area, population and value addition, or GDP, had unintended and negative consequences elsewhere. And that's why systems thinking and system dynamics are so important, because we can start to identify these unintended consequences and sort of get ahead of them. And one way we do that is through the use of causal loop diagrams or systems mapping. Causal loop diagrams are created to sort of identify the main variables. In this case, it was population, value addition, fishing, so on and so forth, and then try to understand the main dynamics of the system. Now, this is usually done through a co-creationary exercise. So we have many people in the room to try to create a common understanding, to then sort of capture the mental models of these individuals or teams to create a common understanding or shared hypothesis about the causes of these dynamics. Now, with that out of the way, let's jump into how this was applied in the SUSTRACK project. So if we're looking on the screen here, we have two variables. In this case, we have demand and production with a blue arrow that's connecting them. This arrow denotes causality, meaning that demand impacts production. What we see then is a plus sign next to this. Now, that plus sign does not denote that it's a good or bad relationship. It simply denotes the directionality. So in this case, because it is a plus, it means that if demand increases, production will change the same way. So an increase in demand leads to an increase in production. If it was a minus, it would be the opposite. So demand increasing causes production to decrease. With that out of the way, let's jump into the narrative. So what we start to see is in a circular bio-based economy, at least if we're considering sort of the baseline, which is a linear economy, the more demand we have, the more production. But as production starts to increase, there will be more employment downstream, upstream, as well as in the factories. So there'll be more employment and therefore more economic growth. People are getting richer, which means they can spend more on clothes, computers, textiles, all of this, which further then starts to boost demand. With higher demand, there's also additional more production. However, there's a certain amount of lifetime per product, right? Products don't last forever. So at a certain point, there will be an end of lifetime discarding, resulting in further demand because people maybe replace their old laptop, buy a new shirt, so on and so forth. What these loops are, they are reinforcing. And what it means by that is that an initial increase in one direction will push the whole system that way. And because we start out with increasing demand, we're going to have more demand, more production, more employment, more economic growth, so on and so forth. But we can also have a limiting factor in the system, and these will be balancing. One specific example in this case is that as we start to have higher levels of production, we'll consume more and more resources. Think of input materials into the chemical sector, plastic sector, plastic and wood into construction, cotton into textile, so on and so forth. All of this resource consumption and extraction leads to higher levels of greenhouse gas emission and air pollution, which means that you might be working in more polluted factories and overall leading to higher cost externalities, which will reduce overall total factory productivity and start to decrease growth. At the same time, each of these processes, so end of lifetime discarding, production, and resource consumption, starts to lead to more and more waste being produced and collected. And now if we're considering the sort of baseline linear system, this might then end up into waste landfills and further increase greenhouse gas emissions. Now this is our sort of, I guess I mentioned, our linear economic system. But what if we didn't want this? We wanted to include, maybe move towards more a circular economy or a bio-based economy. Well, we need to start introducing policies. And in this case, the first policies we looked at was a demand-focused policy, such as trying to curtail demand. This could be, for example, through banning single-use plastics or decreasing the amount of houses someone can own. That means that we'll have less production overall. And if we couple that with resource efficiency, there'll be overall less resource consumption, less waste being generated. At the same time, if we have less waste being generated, but we're increasing the collection rate, we'll have more waste being collected, but we may not want that to be sent to landfills. So we start to consider reusing directly within the factory itself, but then potentially also reusing recycling from the waste into the resource consumptions. So we further decrease resource consumption itself. And at the same time, we cannot forget about the secondary markets, such as, for example, secondhand stores for textiles. So in this case, some of that waste may end up being reused fully as an art, which artificially extends the product lifetime. And we can also, of course, have product design improvements. So in the end, if we're looking at this, this is a very circular-based program as well, but we want to consider bio-based aspects as well. So if we start to shift away towards a more bio-based production, what we'll have is a greater amount of biomass demand. Now, and this is thanks to a lot of the researchers, some of the researchers within the SUSTRACK consortium. And what we find is that if we have greater biomass demand, we actually have enough marginal and banded land use to be able to meet that demand sustainably instead of trying to have impacts on, let's say, agriculture or forestation, which in this case could boost greenhouse gas emission. But in the case that the fact that these are marginal abandoned, there is less impact on further emissions themselves. Now, this is a very material flow focused diagram, meaning you have the materials that flows from demand into production, into waste, and further back into reusing, recycling, so on and so forth. But what if we flip the script on this to try to turn it into more of an economic or financial one? So if we start to consider the fact that a lot of these things are actually cost savings, right? The less resource consumption we have, the less we have to spend on resources, the less product and waste collection we have, the less we have to spend on waste, which means we'll over have a less greenhouse gas emission and therefore higher total factor productivity, which will boost economic growth and therefore demand. And what we find is that all of these cost saving things that start to affect our total factor productivity, leading to overall greater economic growth, offsets some of those initial losses we might have from transition from conservation policies or from greater cost to initial bio-based products. With that being said, we'll now move into the more quantified aspect of system dynamics and the actual application to it within the SUSTRACK project. So in this case, to be able to measure and monitor the green forecast, the circular bio-based economy, what we used was the green economy model, or GEM. Now, GEM estimates the outcomes of macro-level sustainable transitions, so mitigation and adaptation, both for selected countries as well as the EU level, and has been applied in over 50 countries, mainly focusing on LP-LEDs, NDC updates, green economy strategy, so on and so forth. What makes this application unique is that we integrated an industry model into the green economy model so that we could forecast both sort of national macro assessments, but then also be able to monitor this current trends within the industry themselves, and so that they interact together. What we can then do with these results is that we can group them in a systemic cost benefit analysis that includes both tangible, so additional value addition, so on and so forth, with intangible outcomes such as carbon pricing. Now, what this model is also built in Vensim, which means that each of these variables generates a graph for themselves, even intermediate ones where, for example, we're converting from kilowatt hours to megawatt hours. So what we can do is that each of these investments that are made that we're forecasting to see the outcomes of, we can generate a storyline and follow that along to see where the reducing costs are, where the benefits are being generated over time. We can then use this, or we did use this, to forecast national and industry trajectories under various scenarios. Getting a bit deeper into how exactly this worked. So as I mentioned, we did couple together both of these models. So what we had is the green economy model at the top that forecasted population, power mix, emissions factor, primary, secondary, and tertiary sectors, so on and so forth, government accounts. And what we then send is all relevant indicators from there. So for example, population, power, emission factors. They are then sent into the industry model so that we calculate demand. And we then send all of that demand through the processes we went through in the causal loop diagram. So demand, production, recycling, reuse, and so on and so forth. We then take this energy consumption, we take the emissions, and we especially take the sectoral value addition. We put that back into the national environment or the green economy model so that changes done on the green economy or the national level, such as, let's say, we reduce population, will be felt in the industry and vice versa. Now, it's important to note here that the output indicators, both on the green economy level as well as the industry level, are generally aligned with the monitoring tool that was presented in the previous session. So some of the scenarios that we generated over time, we did sort of three, but we did, how would you say, various takes in each of them. So we had the baseline scenario, which is our business as usual. And this assumes that the current trends continue in the future with no ambition of circular bio-based economy. Effectively, if you're at 95% recycling today, you will be at 95% recycling until 2050. The next scenario we did was the biotransition, and there we did a literature review of all status quo policy objectives, meaning that if the EU projects or has a policy where recycling rates need to be at 100% by 2030, that is then what we simulated in a biotransition scenario. We then moved into the biorevolution scenario, which then tries to see if we are more ambitious and earlier to see what the impacts will be. Effectively, we move on from if we did nothing to where we're going and what if we did more by the time we get to the biorevolution scenario. Now, this is just to provide some of the key messages that we have found. And of course, I won't dive into everything. We have a report that we would love for you to read that dives deeper into the results, the model structure, and everything. But this is just an example of what some of the results that can be produced with a system dynamics model when applying it to circular bio-based economies. The first thing we find is that the value addition for bio-based products end up greater eventually is when you start considering reducing externalities, as well as also directly because of that overall increase in the bio market. Additionally, we also find that even with lower consumption, so let's say banning single-use plastics, eventually the circular bio-based economy value gain offsets some of these losses so that overall you have a more value industry in the end. We also find that we can meet biomass demand sustainably if we use marginal abandoned lands to avoid deforestation and preserving prime agriculture. We find that biomass needs can be met with either a third or half of all available marginal lands within each of these countries. So this was applied to Germany, Netherlands, as well as Italy, to ensure that there's no compromise on food production nor increased deforestation. This is especially important considering that we're in the middle of the NBC update, with land being a large factor of carbon sink. So if you want to meet our climate mitigation targets, land plays a crucial role in this, and especially more carbon-dense lands such as forest. And lastly, which is more of a general point, is that often with system dynamics, you have to look at the trade-offs and policy implications, meaning that there has to be a balance between these economic benefits as well as land and environmental pressures that can occur. For example, if we need to start using more forest, which would mean that in these sort of sectoral shifts, we need additional policies to be able to support them, such as in this case, sustainable land management, to be able to mitigate some of those ecosystem impacts. Another thing that needs to be considered is that our findings suggest that there is an increase in jobs overall, but these are different jobs, meaning that certain industries or certain sectors will experience some pain, and there needs to be policies to be able to support that going forward. And lastly, just to provide you some additional value propositions on the use of system dynamics and systems thinking. The first one is that one of the key benefits of using a more systemic type of modeling or methodology is that we can analyze any potential side effects and synergies that emerge from the implementation of these strategies and investments, so that we can capture and plan ahead before we start to see, for example, the job loss or increased deforestation. Additionally, if they're done through a co-creation or exercise, we can create a shared understanding of the changes that are introduced by these policies, so that if they are done together in a room, there will be less misunderstandings and conflicts among stakeholders. This holds true in our experience as well within the literature. And lastly, we can assess the magnitude of impacts across social, economic, and environmental indicators that can then be informed these strategies, so that there's monitoring and evaluation. At the same time, because especially when it comes to these very encompassing strategies, it's important to note that we cannot measure everything, and therefore there has to be sort of collaboration both from farmers, any industry that may be impacted by such strategies, such as farmers, workers, recycling, landfill, so on and so forth, so that again you can have a more just and fair transition overall. Thank you very much.